Hello everyone, welcome back to the Concepts of Engineering Mathematics course. In the previous lecture, we had seen the matrix multiplication. We also saw some of the properties of matrix multiplication, and then we had seen the concept of adjoint of a matrix. And with the help of adjoint, how we can find inverse, we also saw that. Okay. And after that, we started uh, the solution of simultaneous equations using matrix method. And in that, we saw the rank of a matrix and consistency of system of equations, both for non-homogeneous and homogeneous. Okay. So now let us solve equation or a system of equations using the matrix method. We are given with a system of equations. So say we have to solve the following system of let us modify the problem statement that first let us check the consistency of the system of equations, and then if solution exists, then we will proceed for the solution. So check the consistency of the following system of equations and solve them if they are consistent using the matrix method. Using matrix method. So the system of equations are means the equations which are given are x plus y plus z is equal to 3. This is the first equation. Then next one is x plus 2y plus 3z is 4. So x plus 2y plus 3z is 4. Then next equation is x plus 4y plus 9z is 6. Okay, so x plus 4y plus 9z is 6. Okay, so these are the three equations. So now let us proceed for the solution. So firstly, we have to check the consistency, and for that we need to form the augmented matrix, and then we need to find the rank of the coefficient matrix and augmented matrix, and then only we can say anything about the consistency. Okay, and it is obvious from the given equations that this is a non-homogeneous system where right hand side is not 0. So firstly, the coefficient matrix is given as this is given as 1 1 1, and then we have 1 2 4. Then the coefficients of z are 1 3 9. So this is the coefficient matrix. Variable matrix is x y z, and then we have the matrix of constants. So this is 3 4 and 6. So from these matrices, we can write the augmented matrix as, so say A is our augmented matrix. Augmented matrix A will be augmentation of M and K. So this will be nothing but this 1 1 1, then 1 2 4, and then 1 3 9, and then we have new column as 3 4 6. So this is our augmented matrix. So now we need to find the rank of this A and M. So let us first check for M. So if the determinant of M is not equal to 0, then its rank will be 3 because it is a 3 by 3 matrix. Okay. And we know that rank is the order of highest order non-zero minor. So here highest order minor will be this 3 by 3 minor. Okay. Means the matrix itself, determinant of the matrix itself. So now determinant of M, let us see. This is given as simply this will be 1 into 18 minus 12 minus 1 into 9 minus 3, then plus 1 into 4 minus 2. Okay. And this comes out to be, this is 6, then 9 minus 3 is again 6, so this is minus 6, and then 2. Okay. So this is the value of determinant of coefficient matrix. So this is 2. Now since this value of determinant is not 0, therefore rank of M is 3. Okay. Similarly, we need to find the the rank of augmented matrix, and since the rank of M is 3 and M is one of the minors of augmented matrix, so obviously the rank of the augmented matrix will be 3 only. Okay. Because see here, this is one of the minors. So let me draw a line lately. So this is one of the minors of augmented matrix. Okay. And obviously its value is not 0. So definitely the rank of this augmented matrix will also be 3. Okay. So and since M is a determinant, M is a minor of A, thus rank of A is nothing but 3. And also here the number of unknowns, was also, say this is N, so this is also 3. Okay, so since rank of M is equal to rank of A and this is equal to N and all are 3, therefore the given system of equations is consistent and has a unique solution. If you remember the consistency rules that we saw. So therefore the given system of equations given system of equations is consistent with a unique solution. Unique solution. So now let us see the solution of this system of equations. Okay. So now we know that m into x is k, or we have seen that if we pre-multiply by m inverse, then we get x as m inverse k. So say this is equation A. Okay, so in order to find the solution or values of the variable matrix x, we need to find the inverse of this matrix M. Okay, so for that we need to find uh, the adjoint of M, which will be the transpose of the cofactor matrix, and then we need to divide it by the determinant of M, which is 2. So let us see what are the cofactors. Okay. So let me write the matrix again. So M was 1 1 1, okay. 1 1 1, okay, and then 1 2 4 1 3 9. 1 2 4 1 3 9. Okay. Therefore, the cofactors are given as let us say M subscript C 1. Okay, so this is the first cofactor. So this will be minus 1 to power 1 plus 1, that is positive sign will be there, and we will delete the first row and first column and then find the value of remaining minor or determinant. So that will be nothing but 18 minus 12, which is 6. So this is plus 6. Then we have MC2S. This will be with the negative sign. Okay. And since all values are positive, so sign that comes due to power of 1 minus 1 will be kept as it is. So this is negative of 9 minus 3, again 6. Okay. 18 minus 12 was 6. Okay. Now this is MC3 is positive. 4 minus 2 is 2. Okay. Then we have MC 1 1. This was 1 2. And say this is 1 3. This is 2 1. So this will be negative of second row deleted, first column deleted. So 9 minus 4 is 5. Then MC2 will be positive of 9 minus 1 is 8. And then we have this MC23 as negative of 4 minus 1 is 3. Then MC31 is positive of 2, 3 minus 2 is 1. Then we have MC32 as 3 minus 1 is 2, and this is negative. 3 minus 1 is 2, and then we have MC33 will be positive of 2 minus 1 is 1. So therefore, the augmented matrix, not the augmented matrix, basically the cofactor matrix of M is given as MC. This is nothing but 6 minus 5 1, then minus 6 8 minus 2, and then 2, -3 and 1. So this gives us the cofactor matrix of M. Now to find the adjoint, we need to take the transpose of this matrix. Okay, so therefore adjoint of M is nothing but MC transpose, and this is nothing but 6 -6 2, then -5 8 -3, and then 1 -2 1. So this gives us the transpose. Now we have the value of adjoint, so we can now find the value of M inverse. Okay, and determinant of M was 2. Okay, so here we had calculated the value of determinant, and this was 2. From here we can see. So let us now find write the value of inverse. Therefore, M inverse is nothing but this adjoint of M divided by determinant of M. Or we can say that transpose of cofactor matrix of M divided by determinant of M. And this is nothing but the determinant is say 1/2, and the matrix here is 6 -6 2, then -5 8 -3, and then 1 -2 1. Okay. So now we have the value of M inverse. Okay. So using this, we can now find the value of X. Okay. So let's say this is equation number B. Okay. So from this B and A, we can say that thus X is M inverse K. So let us write the values. So X, let us put it as X only. We will later replace it with X, Y, and Z. So M inverse is M inverse comes out to be 1/2. I have kept the scalar outside. So this is 6 -6 2, then -5 8 -3 1 -2 and 1, and then we had the matrix K, which is the value matrix found by constants. So this was 3 4 and 6. So we have 3 4 and 6. So now let us multiply these two matrices. So this is 1/2, and again row multiplied by column. And since this first matrix is a 3/3 matrix and the second one is a 3/1 matrix, that is there are 3 rows and 1 column only. So the product will have again 3 rows and 1 column. So we have this is 18 -20 plus 6, and here we have -18 plus 32 -12, and then we have 6 -12 plus 6. Okay. So upon solving, we get this is 1/2, and here this becomes this is -2 plus 6, which is 4. Okay, and here we have -18, and this becomes 20 -18, this is 2. Okay, and here this is 6 plus 6 is 12 -12 is 0. Okay. So now we need to multiply this 1/2 with all the elements, since this is a scalar multiplication. So this becomes 4/2 is 2, then 2/2 is 1, and this is 0. Okay. So since this matrix X was nothing but X, Y, and Z, So from here we can now equate these two matrices and get we will get the values of our unknowns. So now we have solved the system of equations. Therefore, x is nothing but 2, y is 1, and z has come out to be 0. Okay, so this is the answer. So this is one of the ways to solve the system of equations using matrix method. Okay. So apart from this method, there is one more very commonly used method of solving the equation using matrix. So let us see that also. So we now have the row reduction method. Row reduction method of solving simultaneous equations. Simultaneous equations. So the check for consistency remains the same. We will only now modify the way of solving. So as the name suggests here, we need to keep reducing the coefficients of various variables in the rows of the augmented matrix, and after we have reduced the coefficients of all the unknowns, means all variables, step by step, we will finally get the solution of equation. Okay, so let us see how this is done with the help of an example directly. Okay. So let me write the steps for row reduction first. Yes, so there are 3 steps basically. For not only 3 steps, basically these are the repetitive steps. They will be repeated for as many variables as we have. Okay. So say we have again a 3 variable system. So we will have 3 steps. That is in first step will reduce. Let me write it also, that for 3 variable system. So here step 1 is to reduce the coefficient of x in row number 2 and row number 3. And reduction means to make them 0. Okay. So we need to make the coefficients of x in the row number 2 and row number 3 equal to 0 when we have kept the variable matrix as x, y, and z. Means in we are first assuming x, then y, then z. In that case, we will reduce the coefficients of x in row 2 and row 3. And then step 2 will be to, okay, these operations we will perform on the augmented matrix here. Okay. Let me write that also. So reduce the coefficient of x in row 2 and row 3 of augmented matrix. Now the next step will be again very similar, that here we have to reduce the coefficients of y in row 1 and row 3 of augmented matrix. Okay, so this is the how it is done. And then In the next step, we need to reduce the coefficient of Z in row 1 and row 2 of augmented matrix. So let us see how it is done with the help of an example. So that will make it much clear. So suppose we are given with the system of equations. So say solve the following system of equations using row reduction. Row reduction method. Okay, so let us take a variable system so that there will be no confusion regarding the number of variables. Okay. So suppose we have the first equation as x plus y plus z plus p equal to 15. This is our first equation. Then we will have x minus y minus z minus p is equal to 2. This is the second one. Then we have say minus x plus 3y plus z plus 2p equal to 5. And this is the third. And we will have one more equation since this is system of 4 variables. So x plus y minus z minus p equal to minus 2. Okay. So these are the system of means this is the set of equations that we are given with. So since here we need only the augmented matrix, so let us directly form the augmented matrix and begin our solution. So here we have say the augmented matrix A is given as, there are 4 rows here. So 1 1 minus 1 and 1. Then we have 1 minus 1 3 and then 1. Then we have 1 minus 1 1 minus 1. Again we have 1 minus 1 2 minus 1, and then this constant terms will also be added to the augmented matrix. Okay, so they will form the next column. So 15 2 5 and minus 2. So in this way we form the augmented matrix. Now we need to perform the row reduction operation. Okay, so let us do that one by one. So we are now reducing the coefficients of x. See here, the first column represented the coefficient of x, second the coefficients of y, and third the coefficient of z, and so on. Okay, so we are now reducing the coefficients of x. Again, here our variable matrix will be in this order of this only. Okay, so x, y, z, and p. So our first variable is x. That's why we are assuming that the first coefficient of first row is of x. Okay, so actually the every value in first column will be the coefficient of x. Okay, so but we will take the row 1 here. Okay, for x. Okay. So reducing the coefficient of x uh, in rows 2, 3, and 4. So for that, what we can do is uh, we know that when we add or subtract a row from the matrix, uh, this operation can be uh, done. Okay, so that will not affect the values or order of the matrix. So let us see how that happens. Okay, so we will now. Okay, also since we are reducing the coefficients of rows 2 and rows 2, 3, and 4, so uh, we cannot use them for reduction of any other row at the same time. Okay, means suppose we are reducing the x coefficient of row 2, then we cannot use row 2 for reduction of the coefficient in row 3 or 4. Okay, so we can only perform the operations using row 1, because here row 1 we have kept unchanged. Okay, so we will reduce the coefficient using row 1 only. So what can be done is we can uh, we can say row 2 minus row 1. Okay, so this will reduce the x coefficient of row 2. Okay, then next we can for row 3 we can add the row 1. Okay, so row 3 plus row 1. Okay. And then for row 4 we can again subtract. Okay, so row 4 minus row 1. Okay. So this results in. Okay, so let us correctly put it here. So how it appears is this remains unchanged. So 1, 1, 1, 1, 15, and this gets reduced. So row 2 minus row 1. So this is 0. This is minus 2. Again, this is minus 2. This is again minus 2. And this becomes minus 13. Okay. Similarly, here we have added. So this becomes 0. This becomes 4. This is 2. This is 3. And then we have 20. Okay. And here in the last row, this will be subtracted. So 0, 0. This is minus 2. And this is minus 2. And this becomes minus 17. Okay. So here we have completed the first step. That is, we have reduced the coefficients of x in row 2, 3, and 4. Okay. Now we will reducing the coefficients of y in row 1, 3, and 4. Okay. In rows 1, 3, and 4. Okay. So for that, what we need to do is see here the row 4 has already the coefficient of y as 0. So we only need to do the operation on row 1 and 3. Okay. So what can be done is we can now say that row 1 will now be if we add half, as I mentioned, we can only use the row 2 for reduction. Okay, so if we add half of row 2 to row 1, then this will be reduced. And again, for row 3, what we need to do is we can add twice of the row 2 to row 3. So the y coefficient will be reduced. Okay, so this is twice of row 3. So this will result in Okay, so this is row 1 is half of row 2 added. Okay, so here nothing will change. So this is 1. This becomes 0. Then we again have 0, and again we will have here 0. Okay, so this will be now 17 by 2, because we are adding half. So this will be 15 minus 13 by 2. So this will be 30 minus 13 upon 2, which will be nothing but 17 by 2. And this row remains same or unchanged. So this is kept as it is. Then we have reduced the third row. So here again we have 0, 0. Okay. And again here we will have minus 2, because 2 minus 4 is minus 2. And this will be minus 1, 3 minus 4. And this will be minus 6. Okay. Because 20 minus 26 will be there. And again fourth row is was already correct, so we did not change it. So this remains the same. So in this way we have now reduced the coefficient of y in row 1, 3 and 4. Now we need to reduce the coefficients of z, and that will be done in row 1, row 2 and row 4. Okay. So reducing the coefficient of z in rows 1, 2 and 4. So for this, how it can be done? Let us see. So now, since in row 1, it is the coefficient of z is already 0. So we need not to do any operation over there. So let us do for row 2. So what we can do to row 2 is we can simply subtract the row 3 from row 2. Yeah, and that will reduce the z coefficient here. And for row 4 also, we can do the same, that we can subtract it. Okay, so because minus 2 subtracted from minus 2 will be 0. Okay, so this will be row 4 minus row 3. Again, for the reduction, we are using row 3 because we are not going to change the row 3 in this step. Okay, so this now becomes this is 1, 0, 0, 0, 17, 17 by 2. This will be unchanged. What is that? So 17 by 2. Then we will have here 0, row 2 minus row 3. So 0, this is minus 2. This again becomes 0, and this becomes minus 1. And then here we have minus 13 plus 12 will be minus, okay, sorry, not plus 12, plus 6. So minus 13 plus 6 will be minus 7. Okay. Then we have third row is unchanged to 0, 0, minus 2, minus 1. And this remains minus 6. So row 4 minus row 3 we had done. So this is 0, 0. This again is 0. And then we have here minus 2 plus 1. So this will be minus 1. And here we will have minus 11. So we have now reduced the coefficients of z also. Now in the next step, we need to reduce the coefficient of p in row 1, row 2 and row 3, keeping the row 4 constant or unchanged. Okay. So we are now reducing the coefficients of p in rows 1, 2, and 3. And for this, if we see, the coefficient of P is already 0 in row 1. So we only need to reduce it in the row 2 and row 3. So how can it be done? So for row 2, we can simply subtract the row 4 from here. So row 2 minus row 4. And similarly for row 3 also, we can simply subtract the row 4. Okay, so row 3 minus again row 4. This will reduce the coefficients of P in rows 2 and 3. Okay, so after doing this, what is obtained is this remains the same 1 0 0 0, then 17 by 2. Okay, and then we have now subtracted 4 from row 2, means row 4 from row 2. So this is 0, this is minus 2, this is again 0, this has been subtracted, so this is 0, and this has now become 4. Okay. And because minus 7 plus 11, so this will be 4. Then row 3, again row 3 minus row 4 is 0, 0, minus 2, this is 0, and then here we will have 5. So minus 6 plus 11 is 5, and row 4 remains unchanged. So we have completed the reduction for all the 4 variables. Okay. So we now have a matrix which is in the reduced form. Okay. So since this was the augmented matrix, now we can split it and we can write it in the form of product of this coefficient matrix and variable matrix will be equal to the constant term matrix. Okay. So we can say that this 1 0 0 0 0 minus 2 0 0 0 0 minus 2 0 0 0 0 minus 1, and if this is multiplied with x y z e, okay, then this is equal to this last column of the matrix, which is 17 by 2, 4, 5, minus 11. Okay. So we, in fact, we have solved the system of equations by just reduction of rows. Okay. Now, if we multiply these, we will simply get a column matrix. 4, since 4 by 4 matrix is being multiplied with 4 by 1 matrix, so resultant will again be a 4 by 1 matrix. Okay. And this will be x, everything will be 0. Here it will be minus 2y, other terms will be 0, so minus 2y only. Here minus 2z, and here we will have minus p, and this is equal to 17 by 2, 4, 5, and minus 11. So by equating the terms, we can now write the values of variables. So x comes out to be 17 by 2, and minus 2y is 4, so y comes out to be minus 2. Okay. And similarly, minus 2z is 5, so z is minus 5 by 2, and minus p is minus 11, so p comes out to be 11. Okay. Therefore, we can more clearly write x is 17 by 2, y is minus 2, z is minus 5 by 2, and p is 11. So this is the answer to the given system of equations. Okay. So in this way, we can use matrices to solve the system of simultaneous equations in various variables. So with this, let us close our discussion on matrices and let us start the new topic of vectors. Okay, so let us begin. the new topic about vectors. Okay, so let us very quickly see some concepts related to vectors. Since this is also one of the very important concepts which is employed for various engineering application problems. Okay, so we'll now see something about vectors. So vector is basically a quantity which has both magnitude as well as direction. Okay. So anything which has only magnitude is known as scalar. So we have seen scalars in very detail from our basic classes itself. So let us see something about vectors which have direction along with the magnitude. Okay. So let me write that uh, vector is a quantity which has both magnitude and direction, which has both magnitude and direction. Okay. So there are various examples of vectors, like quantities which have direction are, say, velocity, force, electric field, magnetic field, etc. These are the quantities which have some magnitude as well as they have certain directions. Okay, so they are vectors. Okay, so some examples are velocity, force, electric field, intensity, etc. Okay. Intensity, etc. So these are some examples of the vector quantities. Okay, so as compared to these vectors, scalars are those which have only magnitude and they do not have any direction, like speed, okay, speed or mass. So let us now see how a vector is represented and resolved. Okay, so we have say a system of coordinate system. Suppose we have x and y. Okay. This only we can use to represent the direction. Okay, so suppose if from the origin we are measuring the distance of any object or anything, so to locate its direction, we can say that how many units it is in the x direction, and then we can check then that how many units it is in the y direction. Okay, so in that way, the direction will automatically come into consideration, and magnitude will be the distance between that object and the reference point. Generally, it is origin. Okay. So suppose we have a point here, okay, and its coordinates are x and y, and it is like this. So if we joined it with the origin, so this is x and this is y. Y. So here, this is something known as the vector. It has magnitude of say r. We will see how the magnitude is calculated, and the direction is represented by this arrow. Okay. So the tip of the line which has the arrow sign is known as head of the vector, and the other end which does not have any arrow is known as the tail of the vector. Okay. And the direction is from tail to head. Okay. So suppose this makes angle theta. So this angle will be used for its resolution. Okay. And these are its intercepts, or we can say projections on the respective axis. Okay, so say this is its magnitude is Rx, and this distance is Ry. Okay, so as I said, to locate this point, we can say that this point is located at a distance Rx in the x direction and at a distance Ry in the y direction. Okay. So if we write both of these things jointly, then it will be in the form of a vector, and it is written as, this is the way of representing a vector. We place arrow over the alphabet which represents the vector quantity. Okay, so vector R is given as, for the coordinate axis we use unit vectors known as I cap, j cap in the two-dimensional system, and I, j, k cap means I cap for x, j cap for y, and k cap for z axis in the 3D system. So here we are dealing with 2D. So this is Rx, the magnitude, multiplied by the direction plus the other direction, contribution of other direction, which will be Ry into j cap. Okay, so in this way we can represent a vector quantity. So here we have both magnitude as well as direction. Okay. And from geometry, it can be observed or can be concluded that the magnitude of this Rx and Ry are nothing but the projections of this length, say R, or let me represent this point with alphabet A. So the distance OA is the magnitude of this vector, and these quantities Rx and Ry are nothing but the projections of this OA on the respective axis. And this method of writing them in the resolved form is known as resolution of vectors. So this can be resolved as, let me change the ink color. So this is Rx, this will be nothing but cos theta. Okay, simple geometry it is. And again Ry can be written as, this is magnitude multiplied with cos theta. Okay, so R cos theta. Okay, say this distance is R from OA. OA is nothing but R. Okay. So this is R sin theta. So this is the resolution of these vectors. Okay. And if we want to write the magnitude only, then it is given as square root of Rx square plus Ry square. Okay. This is nothing but the length of vector R. We will not go into the derivation. If you wish to derive it, you can apply simple geometry and Pythagoras theorem to the triangles OA and say these are BC. This point is say B, this is C. So using simple geometry, we can see that OA will be the sum of square, means it will be the square root of sum of squares of OB and AB. Okay. So this is the length of vector R, and it represents this symbol, means mod symbol represents the magnitude of the vector. And in 3D also we can write the magnitude. So in 3D, again the magnitude is given in a similar manner, only there will be an additional term for the z axis. So this will be Rx square plus Ry square plus Rz square. Okay. Simply it is extended to the 3D form. So in this way, the vectors can be represented and resolved. Okay. So also there is an important concept known as the unit vector. So unit vector is, as the name suggests, will have a magnitude as unity. So it is only used to represent the direction. Okay. So any unit vector represents the direction in which it is there. Means suppose if we write the unit vector for OA, then that the unit vector will represent the direction of OA and its magnitude will be unity. So to do that, what we to find that, what we do is we divide the vector by its magnitude. Okay, so that cancels out the magnitude part and only direction remains. And this unit vector is represented by a cap symbol. Okay, so in place of arrow, we put a cap now. So suppose we want to write the unit vector of OA. So this is represented as OA cap, and this will be equal to vector OA divided by its magnitude. Okay. So this is magnitude of vector OA. So this is the method to find the unit vector. And this unit vector represents the direction of OA. It will always have its magnitude as unity. So now let us see the way of adding two vectors. Okay. So vector addition. We will now see addition of vectors. Okay, addition of vectors. So to do the addition of vectors, we simply add the respective components. Okay, means the component of x direction will be added to the x direction component of other vector, and similarly the component of y will be added to y and component of z to z. Okay, so we will proceed in this way, and using the same methodology we can add any number of vectors. Okay, so suppose we have vector r1 and r2. So if we have vector r1, say this is r1 x I cap plus, okay, so you again here we are writing this I cap j cap. So cap symbol represents that these are the unit vectors and these are standard. So I cap means the direction of x axis, j cap for y, and k cap is for z. Okay, so r1 xi, this is the x component, and then we have say r1 y, r1 y j cap plus r2, sorry, this is r1 z k cap. Okay, so this is vector r1, and similarly say we have a vector r2. This will be nothing but r2 x I cap plus r2 y j cap plus r3 z k cap. So their summation will be nothing but the sum of the individual components. Okay. So vector r1 plus r2 will be nothing but x gets added to x. So r1x plus r2x I cap plus r1y plus r2y j cap plus r1z plus r2z k cap. Okay. So in this way, the two vectors are added. Okay. So let us also see geometrically how this happens. Okay. So suppose we have a vector A like this. Okay. This is vector A, and we have say another vector somewhere here. Vectors can be placed anywhere in the space, and any vector parallel to the given vector will represent the same direction, and if it has a similar magnitude, then both the vectors are said to be equal. Okay. So if the direction of two vectors is same, or say they are parallel and they have same magnitude, then they will be equal. Okay. So this means that vectors can be shifted anywhere. Okay. So this is say vector B. Okay. So when we add them together, what we basically do is we place the vector B, we place the tail of the vector B over the head of the vector A, like this. Okay, so this was vector A and this is vector B. Okay. Now here if we join the tail of first vector with the head of the second vector like this, let me use some other color. So this will be better to understand. So say we now join this tail of vector A with the head of vector B, then this new vector formed will represent the summation of vector A and B. So this will be vector A plus vector B. This is how it is done geometrically. And many times this method is known as triangle law of vector addition. Okay. So if you perform this using the coordinates, then also you'll get the same result, that this represents the summation of the vectors. And the sum vector summation or addition of vectors is commutative. Okay. So that will be providing the same result. So suppose if we add vector B to A, this is vector A plus B. If we write vector B plus A, then how can we write that? Let us see. So to do that, we now need to put the vector A on the head of vector B. Okay, so that will be done in a manner. So say this was our vector B. Okay. And now we will put the vector A here, like this. And again, if we join the tail of first vector to the head of the second vector, you can see that again we get a vector of similar magnitude or as that of vector A plus vector B, and direction is also same. And as I have mentioned that if the magnitude and direction of two vectors are same, so they are basically equal. So this was our vector A and this is vector B. So now this new vector represents vector B plus vector A. Okay. And from here we can say that vector A plus B is same as that vector B plus vector A. Okay. So this means that the vector sum is commutative. Okay. And in a similar manner, the subtraction of vectors can also be done. Okay, so let us quickly see how basically the negative of any vector represents the opposite direction. Means suppose if we write negative of vector A, then it will get reversed in the direction. Okay. The head will become tail and tail will become head. Okay. So simply gets reversed in the direction. So that's why we can now write vector A minus vector B. Okay. This difference also follows the same method, means the respective components are subtracted from each other. Okay. So it means that vector A minus vector B, if we write, then x component of B will be subtracted from x component of A, and y component of B from y component of A, and so on. Okay. So geometrically, how it is represented, let us see. So here we are writing vector A minus vector B. So we will keep the vector A as it is, like this, and we will now reverse the direction of vector B because we have now written minus vector B. So vector B will become something like this. So this is vector A and this is negative vector B. Magnitude will not be changed, only direction will be reversed. Okay. So what will happen if we want to represent the difference? Then automatically, if we say like we we put the vector A like this, and we put the vector minus B like this. So this is vector A, this is negative of vector B, and if we join them, again applying the vector law, we can say that this is vector A plus negative of vector B, which is nothing but vector A minus vector B. This is how the difference is determined. Okay. So this is the way of addition and subtraction of vectors. So let us stop for now, and in the next lecture we will see the multiplication of vectors, okay, or how the product of vectors is obtained. So thank you everyone.